to Calculus 2. I know it's boring, every single one starts like that, but such is life. So, improper integrals. This section is going to be a life-changing event, because since you're sitting in the Calculus 2, you will be integrating your whole life. And since you are working on the application, you will be integrating with limits, which means definite integrals. Improper integrals only affect definite integrals. And this is a life-changing event because you will have to be careful from today on. Anytime you see a definite integral, you will have to check first if it's improper and then go and solve it. So we all know that integral 2 to 4 of x dx is nothing special, right? You can just compute it. But after this lecture, every time you see this, right, definite integral, you will have to stop at least for a second and think whether it's proper or improper. We're going to have two types, type 1 and type 2 improper integrals. And it's type 2 that it's scary, because you might be tempted to go and compute this integral because it's nothing special, right? You know how to integrate 1 over x and you just compute at limits. Well, the issue is there's a vertical asymptote right in the middle. So if you draw your 1 over x, right, you see that the area leaks this way and that way. And that could cause infinite area, and you would calculate maybe something finite. So you see how the whole thing could be wrong. So we are going to, I meant to say a square over here, 1 over x squared. So, gotta switch the graph as well. So we'll have to address that stuff. So we're going to have type 1 improper integrals and type 2 improper integrals. Type 1 will have infinity somewhere in limits. So guys, if you have eyes, you will immediately see that, all right? Whether it's negative infinity or positive infinity in one of the limits, you will see it. So that one you can spot right away. Type 2 improper integral has a vertical asymptote in the interval. Has a vertical asymptote. No, we don't worry about it. Has a vertical asymptote in the interval. And that's the scary one, because you might miss, if you're not careful, you might miss it. Let's talk about type 1, the easier type, tonight. And then on Wednesday we are going to cover type 2, and we're also going to cover differential equations, the introductory lecture. And we're done with the chapter. So type 1, improper integrals. To illustrate how this works, let's take a look at function f of x equals to x, and we would like to calculate area under the curve from 3 to infinity. Well, we could graph. This is where 3, let's say, is. And then infinity is this way on x-axis, right? So we're looking for this area here. It's clear from the picture immediately that the answer must be infinity, right? And we will call that divergent because it doesn't converge to a value. It's divergent. So we will set immediately the integral. We know that area is computed as f of x dx. So I have x dx, and the limits are 3 to infinity. So this infinity in the upper limit is a clear indication that we have improper integral. The way to solve improper integral is to replace that infinity with a finite value, in this case b, because it's the upper limit, and then you send that b to infinity in the limit. So, limit b goes to infinity, the integral 3 to b x dx. You see what I did? So all I did is instead of infinity, I wrote b and then sent b to infinity. That's because that integral I can solve. If this is a finite value, like 7 or 13 or whatever, I can solve this integral then. But I will solving it for b, and then when I'm done computing the integral, then I apply this limit and send that b to infinity. If it's a lower limit, negative infinity, it would be a goes to negative infinity, and you would have a on the bottom. We'll do the example of that as well. So what's the integral of x? Ox. Now make sure you copy this limit every single step, because it's going to be -1 on every single step you miss. Yeah, you can go negative. If the problem has 11 steps and you forget the limit 11 times, you have -1 for that problem. It's worse than SATs. So here it is, writing limit again because I haven't used it yet. I have b squared over 2 minus 9 over 2. And now when I send b to infinity, everything just blows up, explodes, and we say diverges. I like to put a capital D in the circle for divergent. So I really hope that you guys will spend a long time tomorrow reviewing your limits. Right? You gotta know your limits. Let's take a look at the integral 1 to infinity of 1 over x dx. Limit b goes to infinity of, now what do you think? Would it converge or diverge? So we are looking for this. We know that area is going to leak forever this way. Let's see. So integral 1 to b 1 over x dx. What is the integral there? ln absolute x from 1 to b. So limit b goes to infinity, ln b minus ln 1. How much is ln 1? Think. And how much is ln of infinity? Infinity. Yes. Divergent. Realize the graph, it's the y value. As x goes to infinity, this y will always go up, right? And to the right, so it's also going to infinity. Awesome. Integral 1 to infinity of e to the minus x dx. Look at this one. Area leaks this way, we're going to infinity, starting at 1. Convergent, divergent, what do you think? All right, do it. You have 0? Does the area look like 0?
Look like it's like 0.
Approaching 0?
Negative e.
Negative e? to the negative first. So 1 over e. It should be just 1 over e. Minus and minus, right? So this is going to be called convergent. And you can take the calculator, divide 1 by e, and figure out what the decimals are, floating about. But we do the limit. B goes to infinity. The integral of e to the negative x is going to be negative e to the negative x, computed from 1 to b. We have limit. B goes to infinity of negative e to the negative b plus e to the negative 1, because I have the negative there. So now b is, and when you put infinity up here, this term goes to 0, right? Because e to the negative infinity is 0. Fair? Good. So all we get here is 1 over e, and that is convergent. So area is convergent. It's converging to 1 over e, even though, as you can see clearly right there, the area is leaking, right? Forever. That gap will never close because the exponential function will never touch the x-axis. So that's true. So it's very interesting, right, to see that a gap that will never close, never, will actually produce the finite area, and that finite area is 1 over e. Now you've seen these applications of these actually in other coursework. If you have ever seen the bell-shaped curve in statistics class, the normal curve, that curve actually has 2 of these leaks on both sides, this way and that way, and the area underneath it is 1. And we do not teach at RV calculus-based statistics, but if you go to a school that does have calculus-based statistics, it is exactly this section, improper integrals, that is used to prove this thing. So you've seen applications of this, even though you haven't realized it yet. Eventually you will. Yes, ma'am.
Wait, so does that mean it's infinite area or finite?
It's finite. For the bell-shaped curve is finite.
So is the is the volume also, like if you rotated it, would that also be finite?
Very good. You just created more work for yourself, but you will eventually do it. It's an excellent problem to tie in 2 chapters together for maybe final exam or something.
I'm sorry.
Just to save you some trouble, no, I will not use his example, so you're safe. At least while here in public. Okay, so what happens if we have a case where both ends have infinities? You would have to invoke, so we don't have to do it, actually we can just sketch how it's done. So if you have infinities on both ends, you would actually have to use the theorem from chapter 5, which says that the definite integrals can be interrupted at any point. So you can interrupt this at some convenient value, let's say 0. So you will have a half of the integral done negative infinity to 0, and then another portion of it 0 to, it's not exactly half, but negative infinity to 0 plus 0 to infinity. Because you can't put two limits for the same integral, right? You need to have limit a goes to negative infinity and b goes to positive infinity. You can only put one in front, right? So you split this interval anywhere. Maybe pi would be more convenient. Maybe e would be more convenient. Maybe 1 would be more convenient. Maybe 0 would not be convenient. I don't know. You split it anywhere, and then you will be able to say limit a goes to negative infinity integral, let's say a to 0, and then blah, 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 whatever is there, plus the limit b goes to infinity 0 to b, and then blah, blah, whatever the rest is for the integral. So this is the way how you would deal with if both ends had. And I noticed that our textbook actually doesn't have this case at all. But if you open the Larson book, you will find them. Yes?
Is there like a rule in like chapter 5 that says that if integrals are like symmetrical, you can just multiply by 2?
Yes, but these are infinities, so unfortunately we shouldn't be playing with fire. Infinities are not, you cannot say, you see, L'Hopital rule, remember how we subtracted 2 infinities, got 3/4, got 1/2, depending on the function? What's going to guarantee that the functions are so perfectly symmetrical, right? So we're just going to be careful. And the good part about this, guys, is that since this was the same integrand, the same f of x goes in here and here and here and here, so you are not integrating two different things. This part would be exactly the same. Integration for both is identical. It's just that you will be computing that whatever you find and different, right, limit on this side and a different limit on that side. But the calculus part of integration is identical for both. Fair? That's it. That's the improper type 1, and we will deal with the second portion of this on Wednesday. Thank you for your attention, and see you on Wednesday. Bye.